Howdy! This is Team Blue. I'm Jose. The rest of my team will introduce themselves as we go on. And we are doing section 10.7, ranking the participants in a tournament. So, here we will define what tournaments are in the sense of this application. Now, what they were in graph theory, because we already did that, so don't worry about it. Don't worry about it. So, the application in this section will be how to use directed graphs and graph theory to properly rank the competitors in a given tournament, whether that be playing tennis or chess or whatever. We will do this by first showing an example that the section gives us. Then we will define a useful theorem, as well as an appropriate algorithm, and some additional exercises that we did. An example of a chess tournament is given above. On the right, you see that Dr. Nikita Barabanov eats when he goes to chess tournaments because he just demolishes people. It's amazing. Okay, now consider 6 players in a tennis tournament where they all play each other. You have player 1 who beats players 2, 4, 5, and 6. Player 2 who beats players 4, 5, and 6. Player 3 who only beats players 1 and 2. Player 4 who beats players 5 and 6. Player 5 who beats players 6 and 3. And player 6 who beat 3. Using this data, we can construct 2 things. We can construct a directed graph where for any arc on 2 vertices, the tail denotes the winner between those 2 vertices. And we can also construct an adjacency matrix where each row represents a player, and an entry in a row receives a 1 if the corresponding player beat the player designated to that column player, as seen above. Now, going through the first approach, you can do it by setting up Hamiltonian paths in the graph. The problem with this approach is that you will have many different Hamiltonian paths, giving you many different winners as you go along. So if you follow this one right above here, you'll see that you have winner as number 3, player number 3, but then you have player number 1 being the winner and 2 others. So it's not a very reliable method to go off of. The approach that we will be studying here is going off of score levels. So here's where we're going to use the adjacency matrix. You must first create the first score level. And the way you do that is you go back to your adjacency matrix and you count up how many ones you have for player 1. It sums up to 4, the next one sums up to 3, 3, 2, 2, and 1. And thus you have your first score level. The second score level is done in a very similar way. You go to your first player, first slot, and you count up the scores from the previous one as to who they beat. So you know that player 1 beats players 2, 4, 5, and 6. So you add 3, 2, 2, and 1 to get a score of 8. You do the same thing for player 2. You know they beat players 4, 5, and 6. So you go off of 2, 2, and 1, and so on. In the third score level, you do the same thing with the second score level, etc. Just like that. The problem is that once you do this, you'll see there's a lot of fluctuation between who the winner is between numbers 1 and number 3. So as a result, we have to use the following 2 theorems. Allison?
Okay, so we first have this theorem. Let D be a die-connected tournament with V that should definitely be greater than or equal to 5. And let A be the adjacency matrix of D. Then A to the D plus 3 has to be greater than 0, which means that every entry is positive. And little d is the directed diameter, which just means that if you take the distance between any 2 vertices, d is the maximum distance between any 2. So to prove this, we're going to use a few exercises and a previous theorem. So by exercise 10.1.8, the ijth entry of A is just the number of directed vi, vj walks of length k and d. So to prove this theorem, we just need to show that for any 2 vertices, and they could be the same one, there's a directed walk from one to the other of length d plus 3. So if you let di just be the distance between vi and vj, since d is the maximum distance between any 2, we can get this inequality here. And that implies that this is true. This one's smaller, so we can just subtract it here and it will still be less. And then adding 3 gets us this inequality. And that's right up here. So there's 3 cases. If we have that this thing is less than or equal to v, then by theorem 10.3, this is what it says. each vertex of a die-connected tournament D with D greater than or equal to 3 is contained in a directed K cycle for K between 3 and V. So Vj is contained in a directed D minus Dij plus 3 cycle by that theorem. And then if you take a directed Vi Vj path, which length, the length is just the distance, together with this, with a walk of length D plus, with this cycle, you can get a walk of length D plus 3, which is what we need. Case 2 is if it equals V plus 1, and then case 3 on the next slide will be if it equals V plus 2. So if it's V plus 1, then by that theorem again, we'll get a V minus 2 cycle, we'll call it C1, and then also a directed 3 cycle, say C2, and then if you just take C1 followed by C2, you can make a directed Vi Vj walk of length D plus 3. And then case 3 is very similar. By that theorem, again, you can just get a cycle there, and another 3 cycle through Vj, and then you get a walk. And that was supposed to be proof box, but it didn't turn out that way. So then we have a definition. A real matrix R is called primitive if R to the k is greater than 0 for some k. And then a corollary that we're not going to prove is the adjacency matrix of A of a tournament D is primitive if and only if D is die-connected and V is greater than or equal to 4. And now Jackson's going to talk about the algorithm.
So we have this wonderful algorithm for determining a ranking in a tournament. So first I'll just state what it is to start. We have step 1 is if we have our tournament D, each die component on 4 or more vertices, rank the players using the eigenvector S bar that's correlated to the largest eigenvalue of the adjacency matrix in which Jose was describing earlier. And then if we have a die component on 3 vertices, all these players will have to be ranked equally. And then step 2, we take these die components in their dominance preserving linear order, D1, D2, Dm, and to put it in layman's terms, in a sense, are a little bit easier to follow terms. If we have I and j for our die components, I is less than j, then every arc with one end in di and one end in dj must have its head in dj. So I'll show this kind of with an illustration of how this works. So we can take our tournament here on 4 vertices, and if we notice here, we have that we're going to have 2 die components, namely the single vertice 4 and the triangle 1, 2, 3. So since we only have this case, we will not be using step 3, or not step 3, step 1, because there's no die components with 4 vertices. Hence, we don't have to use an adjacency matrix to find the largest eigenvalue. So we'll just move to step 2 in ranking terms of dominance preserving order. So by our algorithm, we must break down our tournament into die components, put them in their order for such that we have for each I less than j, every arc with one end in di and another in dj has its head in dj. So if we label our first vertex here, or our die component with a single vertex d1, we can notice that, like I was saying earlier, these arcs are all going to this direction. So the head of each arc from 4 goes to 1, it goes to 2, goes to 3. Hence, D1 and D2 is now the order because of what we've described before. So this is our order, at least. So if we must rank the vertices, or rank the components, then we notice that since D1 had 3 arcs going to it, it means vertex 4 had 3 wins. And by our step 1, we noted that any die component on 3 vertices are all ranked equally. So all these vertices here only have 1 win, so hence our players in our tournament go from ranking from first to last goes 4, 1, 2, and 3. An example with though a die component of 4 vertices will be shown later by Emmeline.
Okay. So for problem 10.1, we were given some graphs and we were supposed to find the ranking of the vertices. So this particular graph is die-connected, which you can just see by tracing through the graph. And since it has 4 vertices, we have to get the adjacency matrix for it. So the ijth entry of the matrix is 1 if the arc between the I and jth vertices has its head in j and its tail in I. And then if it doesn't, the entry is 0, and this is also for any ith entry, because you can't win against yourself. So to calculate the ranking from the adjacency matrix, we have to calculate the eigenvalues and the eigenvectors. And this can just be done with the online calculator, you don't actually have to go through the process. For this particular graph, the largest eigenvalue was 1, and the normalized corresponding eigenvector was this. So from here, the highest entries would be the winners, and so the actual ranking of the vertices in this case would be 1, 4, 2, 3. And so now with this graph, though, it's not die-connected. It has 2 die components, the outside 1, 2, 3, and then just the inside single vertex of 4. And since none of these have 4 or more vertices, we don't have to find the adjacency matrix. For the first die component on 3 vertices, they're all ranked equally according to the algorithm. And then the last one is just 1 vertex, so it wins. And so then we have to look at the 2 different components. And since every arc between the first and second die component has its head in the first one, that means that the first die component is ranked last. So altogether the vertices are ranked 4, and then 1, 2, 3, with 1, 2, 3 being tied.